This video will teach how to do some basic comparisons between groups by using R Commander. The plan is that we will cover independent t-test, match t-test, one-way Anova, factorial Anova, and repeated measures Anova. As you can see, I already opened R Commander and I'm ready to go and select the file. This time I'm gonna get a file from Spss that I have used to illustrate how to play with t-test, and the name of the file is example t-test, so I'm gonna select it and then open the file. Let me show you what the file looks like. As you can see, the file has a variable called group that is divided in two conditions, 12 hours and 18 hours, and it has two dependent variables, std_in and std_in2. For this particular case, I'm going to be using std_in2. The first thing that I'm going to do is to do some summaries of the variables. I'm going to be using numerical summaries, and I have selected std_in2, and I'm going to summarize by using group variable. Statistics that I'm going to select is just the mean and the standard deviation. I'm not going to include anything else, and so with that I will just run the analysis, and you can see that the mean for 12 hours is 4.25 and the mean for 18 hours is 6.25. We have 8 observations in each one of the conditions. The next thing that I'm going to do is just to create a box plot. Once more, I'm going to select std_in as the dependent variable, and I'm going to select group as the grouping variable, and with that I'm going to just put a graph title that will be independent t-test, and I'm going to click on OK so we can see the data. As you can see in this chart, we find that there is a large difference between 12 hours and 18 hours. The other thing that we can also see here is that the variances do not seem to be the same for the two groups. So this perhaps should motivate us to try to run some equality of variances test to see if we should use the t-test for equal variances or the t-test for unequal variances. So given that we know that we may have unequal variances, we're going to go into the statistics, and here you will see that there is a variance t-test. So the test that is usually run in this case is the Levine Test, and that is the one that I will be using. I'm going to be using as factors group, and my response variable is std_in2. I'm going to be doing the mean as the center, and I will click on OK. As you can see here, the Levine test is saying that there are not significant differences between the two variances, and so in theory we could just use the equal variances t-test. However, I'm going to try another option and see if we find a different result. The other test that I'm going to be using is the two variances F test. So I select my group, I select my response variable, and I'm going to see what options I have. I'm going to be using a two-sided t-test with a confidence level of 0.95. And so I click on that and I get the result, and the p-value is 0.07. So technically I will say that it is okay to use the equal variances t-test. With that information, all I need to do is to go into statistics, means, and here you will see that there is an option for an independent samples t-test. So I will select that, then my group variable is group, My response variable is steading2. I'm going to check my options. I don't have that many. The only one that I can use different here is to assume that I have equal variances, but you can see that the default is that we do not have equal variances, and perhaps we can run it both ways to see if the interpretation changes. So when we run the analysis using equal variances, we find that the p-value is 0.03. And according to that, what that will mean is that there is a significant difference between the two treatment conditions. I'm going to run the t-test assuming that I have unequal variances, just to double check. So I go back, group, steading in, and now you can see that under options what I will do is to assume that I do not have equal variances, and I'm gonna run the model again. You can see that technically there is not difference between what we got before. We still have a significant result. The value is in fact almost identical to the value that I got before. Next, what I will do is to run a t-test for match samples. And in order to do that, I did some research earlier, and what I found is that there is one specific package that is very well tailored for this type of analysis. So what I'm going to do is to go into Tools. I'm going to load an R Commander plugin. The plugin that I want to load is called MPA Stats. I'm going to do that, and here I get a message that I need to restart. So I'm going to say yes, and then the next time that it opens, you will see that now it has some MPA statistics at the top. So now that I have the options that I want, I'm going to go and import a data file from Spss. The file that I want to load is called match t-test, and let me show you what the data looks like. As you can see, the file has only two variables and they are match. They mean two different measures on the same individual. Just like before, what I'm going to do first is to do some summaries, numerical summaries. I'm going to select the two variables and I'm going to calculate some statistics. Once more, I just want the mean and the standard deviation. I don't want any quantiles. So I'm click on OK, and I get here the values for the means for pay and for security. Next, what I want to do is to plot those two variables, and this is where the new library that we just loaded will be very useful. In this new menu, you will see that we have an option for paired value testing, and so I'm going to select paired t-test, and so I will say that my first variable is pay, the second is security, and you can see that here we have a choice for plot. So I'm going to select that one, and we will have two outputs. One will be the chart, the box plot with the two groups side by side, and I will also have the result of the t-test. The first thing that I'm going to show you is the chart that it generates. So here you can see that we have the distribution for pay, and here we have the distribution for security. You can see that there is some overlap, and so it is possible that we may not have a significant result. Here we have the result of the t-test, and as you can see, this output is a little bit more interesting. It gives you more information than the typical output from R. In this case, it's giving you an explanation. It's saying that it appears that on average pay is different from security. It gives you the true mean difference, and it speaks about the fact that it may be in some confidence interval, and then it will give you the t-score and the p-value for a two-tailed t-test. So according to this test, then we have that there is a significant difference between this pay and security, and that the difference is significant in favor of pay. The regular R commander also has an option to run match t-test, and it is under mean. So here you can see that we have a pair t-test. So we're gonna run that option too. As you can see, the only difference is that in this option we do not have a way to create charts. So let's see what we get, and not surprisingly the two results are identical. In fact, it seems to me that what they are doing in this other plugin is to basically write some information that will help you to interpret what that means, but you can see that the results are basically the same. T equals 2.827, the P is 0.008, the confidence interval goes from 0.32 to 2.0, and then it also speaks about the mean of the differences here, which I don't think that it shows in the part in the previous plugin. So, okay, so that basically covers how to run both an independent t-test and how to run a match t-test. The next thing that we're gonna do is to run an one-way analysis of variance. So once more we are going to go and import a data file from Spss, and the file that we're gonna be using is called example Kirk. And the file that I'm gonna share with you in just a moment looks like this. You can see that this is really an extension of what we did earlier with 12 and 18, except that now we're gonna have 12, 18, 24, and 30 hours. To run an ANOVA, there are again a few things that I like to do as a matter of procedure. I always run numerical summaries so I have an idea of what the data looks like. And once more, I'm going to be doing mean and standard deviations. I don't want quantiles. And we get a sense of the means and standard deviations and the number of cases that we have. So we have 3, 3.5, 4.25, and 6.25 as the means for each one of the different groups. Next, we can create box plots that will have the dependent variable, and we're going to be doing this by groups. We are going to just add as the graph title ANOVA one-way example, and we will run the analysis. So once more you can see that we have difference in terms of 4 groups, and in addition notice that we have an outlier for the 12 hours group. The next thing that we're going to do now is to run once more a test of the variances, and once more we're going to be using the Levine test. We have the mean for group and steady in, and we are going to run the analysis, and here at the bottom we have the result of the analysis. It is important to remember that in this case we want not to reject the null hypothesis. The null hypothesis is saying that the variances for the 4 groups are equal, and if we do not reject it, then we are basically saying that as far as the test is concerned, we do not have enough evidence to reject the null hypothesis that the 4 group variances are unequal. So with this information, now we're going to go and run a statistical test. Means we're going to do one-way ANOVA. We're going to call this one-way example. And we are selecting group instead in. The options is we just want the effect size for now. We will come back and ask for some summary statistics for groups and pairwise comparisons, but for now I just want to know is the main effect, and then also the effect size. So I click on OK, and here at the bottom we have once more the result of the analysis. So this is your typical Anova table. So you can see that we have groups, we have error, here we have the means of squares, the F value, and the P value associated with that. And what we get from this is that there are statistically significant differences between the groups. The other thing that I asked for was the effect size, and here we have eta square. You can see that it breaks that into two pieces, the group eta square and the residuals. Eta square is very similar to R square in regression, and what a potential way to interpret this number is that we have been able to explain about 44% of the total variance by including the groups. So now that we know this, perhaps it's important to remember that the ANOVA is what is known as an omnibus test. So if we have a significant result, all we know is that there is at least one pair or some other combination that is statistically significant from each other. So what we need to do now is to go and run some post-hoc analysis so we can find out where that difference might be. So in order to do that, we are going to go back to statistics, and then we're going to select one-way ANOVA. We're going to call that post-hoc, one word, and we are going to select as the options the summary statistics for groups and pairwise comparisons of means. And now we get the output of that. Notice how by adding those two other options, the printout, the output changed dramatically from what we had before. This is what we got the very first time that we run it. This is what we get now. So we have the means, standard deviations, and the number of cases. We also have specific linear hypotheses. We are basically testing if 18 is different from 12, 24 is different from 12, 30 is different from 12, and so forth. To do that, it's using two-key contrast, and here what we find is that 30 versus 12 seems to be significant, as well as 30 and 18, and perhaps 30 and 24. We are also getting some confidence intervals for the comparisons between the means. So this will be another way to know if we have a significant difference, because if the interval contains 0, then we know that that is not significant. So again, we have here that 30 versus 12 seems to be significant. Same thing for 30 versus 18. So let's go and see if there is any other way to find out what happened. Part of the output that you get when you go and select those options is this chart that shows you the confidence intervals, the mean of the difference, and it has this for each one of the different contrasts that it created. So here will be the line of no effect, and you can see that there are many of these comparisons that include the line of no effect. So in other words, we know that here we do not have an effect. Same thing here. Here's the 30 minus 12 hours, and you can see that the confidence interval do not include 0. And the same thing for 30 minus 18 hours. Again, just a reminder that when we are running an ANOVA, all we know is that there is at least one significant difference, and by doing this contrast and using this chart, we have a more specific idea of where those differences might be. The next analysis that we are going to cover is a factorial ANOVA, and for that we need to go and find a new file. This is a file that I already saved as an RDA file, and it's called Factorial ANOVA R data. And this is what the data looks like. We have the dependent variable attitude, and we have two factors, factor A and factor B. Once more, the first thing that we're going to do is to find some summaries for the information. So we have attitude, and then we're going to be doing a summary for factor A, and these are the scores for factor A, and the same thing for factor B. Once more, we're going to do numerical summaries. We're going to select, and now we're going to select factor B, and here we have the summaries. It would be perhaps be more useful if we had a way to do a combination of the two factors and the dependent variable. And there is a way to do that by going into summaries and then creating a table of statistics. So you can see that I can select more than one factor and I can select the response variable. The only problem is that I can only select one statistic at a time. I cannot select two, as you can see here. I can only select one. So I will do this for mean, and at least we will have a sense of how similar are these mean scores. We can do this again and do now table of statistics for the standard deviations. Hopefully at some point there will be a way to combine these two things into one single table. The other thing that we can do is to create a chart that somehow will show all of this information. So we're going to go into graphs, and then we're going to select plots of means, and then here you see that I can select one or two factors, and I can select the response variable. As my options, I'm going to select the standard errors, and I also want to show the legend to the right of the graph, and then I'm going to put a title that will say Factorial Anova Example. I'm going to click on OK, and this is the plot that we get when we combine these two factors with the dependent variable. So you can see that we have the mean of attitude. Here we have factor A with its 3 levels, and here we have different lines for factor B. A key piece of running a factorial ANOVA is the fact that you are looking for interactions. Finding main effects may be interesting, but really the reason why we run factorial analysis is because we are interested to know if there is an interaction in the dependent variable as far as some of the levels of factor A and the levels of factor B. And the way that we can say that we have an interaction is when we can see that there is a crossing of some of the lines. So it's very likely that we will have a significant interaction in this case. So without further ado, let's go into statistics, mean, and we're going to select multi-way ANOVA. We're going to select the two factors and the dependent variable. We're going to call it factorial ANOVA, and we're going to go into the options and we're going to select the effects size. And here's what we get once that we do that. In the output of the analysis, we find that we have a significant effect for main effect for factor B, and we do have a significant interaction of factor A by factor B. And here we have eta squared, and again eta squared is divided into the different components. You can see that the interaction is accounting for about 23% of the total variance. So now that we got the information related to the main F test, we're gonna go back into the options. We're gonna go back into the options, multi-way ANOVA, and this time we're gonna select summary statistics for groups and pairwise comparisons for means. And we have the output here. Just as it was the case with the one-way ANOVA, when you ask for the breakdown by specific contrast, you get a ton of information. So some of the things that we have here will be, to begin with, the summaries for the two factors combined. Just like I did earlier when I was creating the tables, you can see that here we have the same information for means and for standard deviations. It also gives you the information for the number of cases that you have, and then it will go straight into some form of post-hoc analysis, and it's using once more this idea of the two-key contrast. So the first thing that it's doing is sort of checking for the variable factor b, is checking to see if there are any specific comparisons that will be significant. And you can see here that it's basically saying that there will be a significant differences between 5 and 15 hours. Now, if we wanted to really see what this looks like, we will need to create a new plot where we will collapse across factor b and just to look at the values as collapse across factor a and just look at factor b and calculate and see if we can see the means for the two groups. Now, we're not gonna do that, but if you are interested, it will be just to collapse, like I said, across factor a and just create a new set of box plots to look into that. The next part of the analysis is again doing a bunch of contrast using this two-key contrast approach, and what you can see is that it's basically selecting some specific combinations, for example middle class 10 hours, and comparing that to inner city 10 hours, and then calculating the estimate, the standard error, and the t-value associated with that. And it goes on calculating all of the potential comparisons, and then eventually it will come up with some p-values associated with that. For example, here we find that there is a significant difference between inner city 5 hours and inner city 10 hours, and the same goes for inner city 15 hours and middle class 10 hours. Now, in order to fully understand what some of these values mean, I'm going to switch back to the plot that we created earlier. So we are back in the plot that we created earlier, and just as a reminder, one of the differences that we found were significant was between inner city 5 hours and inner city 15 hours. So this is within one of the factors, but the other comparison that we found was between inner city 15 hours and middle class 10 hours. So this is across two different factors. This, when you are learning and then teaching ANOVA in the more traditional way, we usually speak about simple main effects. This approach, by using the two-key contrast, is going straight into some specific comparisons by creating a specific contrast and then testing them to see if they are significant. So in that sense, this is a step ahead of what you will do when you are doing simple main effects. The main idea behind doing all of this contrast is that you want to be able to come to a full understanding of what creates the interaction. So for example, after looking at all of the comparisons, one thing that becomes clear is that there is clearly a big difference as far as the inner city, middle class, and upper class as far as the effect of the different number of hours. Clearly, within inner city, there is a big difference between 5 and 10 and between 5 and 15, and all of these, which are very different at this level, become non-significant once that you go into middle class and upper class. Just before we move on, I couldn't resist going back and creating a box plot where I collapsed across factor A. And so here we have the specific set of comparisons that were tried earlier using the two-key contrast. So we found that the difference between 15 and 10 hours was not significant. The difference between 5 and 10 hours was not significant, but the difference between 15 and 5 hours was significant. And here you can have an idea of why that may be the case. Finally, we are going to cover repeated measures ANOVA. And I'm going to go over two of the models. One, when you have one factor and all the variables are repeated measures. For example, you can have pre, post, follow-up 1, follow-up 2. And the other where you have two factors and both factors are within subjects. This is, as far as I can tell, one of the areas where R Commander is weak, not so much in terms of the analysis, but in terms of how it displays the data. I did some research and I was not able to find an easy way to do that. But rest assured that if you become more familiar with R and you are not afraid of doing some syntax using the script, you should be able to create very nifty charts. There is a package called ggplot2 which is fabulous, and there is another package called Lattice that allows you to do very interesting charts. Anyhow, so let's just get started. We're gonna import some data from Spss. I do have a couple of examples that I have used in the past for this type of analysis. The first one is this file that contains several variables. As you can see, we have 8 subjects and we have 4 measures: Alt1, Alt2, Alt3 and Alt4. The first thing that we're going to do, as we have been doing in the past, is to create a numerical summary for all 4 variables. And we are going to select as statistics just the mean and the standard deviation. And we're going to click on OK, and here it gives me the mean and the standard deviation for all 4 measures. As I was saying earlier, unfortunately at this point there is not a way to plot these 4 variables in a single box plot or a single plot, and so I will just skip that part and go straight into the analysis. A key assumption for when you are running repeated measures is what is known as sphericity. A quick way to understand what sphericity is about is to think in terms of homogeneity of variance. Under homogeneity of variance, you are assuming that the variances for all the groups that you are including in your analysis will be similar or equal, ideally. The same thing works in this particular case when you are creating, when you are thinking about sphericity. There is no test, as far as I can tell, that you can use just independently within R Commander to test this assumption of sphericity. However, you can run the means repeated measures ANOVA, and in this case we have the factor called ALT that has 4 levels, and we are going to create altimeter 1 will go for the first one, altimeter 2 will be for the second, altimeter 3 for the fourth, and altimeter 4 for the fourth one. Now here under assumptions you will see that we have sum of squares type, and type 3 will have a test called Modulus test for sphericity. So the Modulus test for sphericity is what we want, and we are going to select effect size and then run the model so we can see what happens. So this is the output that we get after we run these repeated measures using type 3 repeated measures. So as you can see here at the top, it's describing type 3 repeated measures ANOVA assuming sphericity. In other words, if our test did not violate this sphericity assumption, this will be the result of the analysis that we just conducted. And what we find here is that there is a statistical significant difference between all four repeated, or at least two of the repeated measures. We don't know which ones. Remember that the ANOVA is an omnibus test. Below, you can see that we have the result of the Modulus test for sphericity. And just as a reminder, in some cases we want this test to be non-significant because that means that we have the null hypothesis is not rejected. In this case, the null hypothesis is that all the variances are filling the assumption of sphericity. Below, you can see that there are two corrections for departure from sphericity. One is known as Greenhouse Geyser and the other is known as Hoyne-Felt. And the way that they work is that they calculate an item called epsilon, and then based on epsilon they will make corrections to the degrees of freedom. And based on that correction to the degrees of freedom, they will recalculate an f value and the p-value associated with that f value. It is said that the Greenhouse Geyser is a little bit more conservative than the Hoyne-Felt correction, and because of that, sometimes it's preferable to use that Greenhouse Geyser as opposed to Hoyne-Felt. But regardless of which one you use, you can see that both of them indicate that the result is significant. So regardless of which one we use, we will know that we have a significant result. Now, the final part of this printout is the partial eta square. And once more, we have here that the factor that we are using is explaining about 62% of the total variance. So now the next step will be to go back into statistics, means, repeated measures, ANOVA. We have this already, and we will select here once more Alt 1, Alt 2, Alt 3, and Alt 4, and we will go into the options. We are selecting again type 3, and then this time we want to select effect size, summarize statistics for groups, and pairwise comparisons of means. So now that we know that we have a significant effect, we can try to do some comparisons to find out which one of the multiple groups seems to be making the difference. This is the output that we get after we run this new version of the analysis. The first thing that we will get is again a summary of all the means, minimum, maximum, and standard deviation for each one of the different repeated measures. And then in the next part we will get once more these two key contrasts that will be basically making a comparison between the different conditions. So 1 minus 2, 2 minus 1, 3 minus 1, 4 minus 1, 3 minus 2, 4 minus 2, and 4 minus 3. And by running this contrast, we can determine that it seems like 4 minus 1 and 4 minus 2 seem to be the two contrasts that seem to be creating a significant effect. Finally, we are going to be conducting a factorial within subjects analysis of variance. In order to run that new model, the first thing that we're going to do is to go into data, import data from Spss, and I have already a file that I know will work in this particular. The name of the file is factorial repeated, and I will select the file. This is the file there that we are going to be using this time. You can see that we have one factor with two levels, dim and bright, and then we have another factor with 4 levels, 0, 2, 4, and 6. The first thing that we are going to do, as usual, is to go and calculate some summary for numerical summaries for these variables. So I am going to select all of the variables, and then I'm going to select the statistics, the usual mean and standard deviation. So I will run that, and I will notice that I have 26 cases, and here I can see that we have a very wide range of means, and so chances are that once more we will have a significant effect. Now remember that when we are doing factorial designs, it's not so important that we have main effects. What is more interesting is to see if we have any sort of interactions. But because we cannot plot that information within R Commander, we don't really know if we have any sort of interaction, so we will have to just hope for the best. The next thing that we're going to be doing once more is to create a repeated measures ANOVA model. And I have two factors. The first factor, I'm going to call it dim bright, and it has two levels. And the other factor, I'm going to call it 0, 2, 4, and 6. And it has 4 factors. Now, the first one is going to be bright 0, bright 2, bright 4, and bright 6. And the second is going to be dim 0, dim 2, dim 4, and dim 6. Now I'm going to go into the options. Remember that because we want to be able to test for sphericity assumption, we need to use the sum of squares type 3. And we're just going to ask initially for the effect size, and we're going to run the model to see what we get. Here we have the result of the analysis, and thank goodness we have a dim bright by 0, 2, 4, and 6 interaction. You can see that is highly significant. Now this is assuming that we have that the assumption of sphericity is holding. And below, as I explained before, we have the Modulus test for sphericity, and you can see that once more, specifically for the interaction, we have that the test is non-significant, which means that the sphericity assumption is holding. Below, as we had in the past, we will have the corrections for departures from sphericity using both the greenhouse geyser and the Hoyne-Felt epsilon correction. And you can see that according to this, for both the greenhouse geyser and the Hoyne-Felt, the results are also significant, so we don't need to worry too much about that. And then finally here we will have the partial eta square for the main effects as well as the interaction. So now, given that we have a significant result, what we want to do next is to go once more into statistics, means, repeated measures ANOVA. This stays as it was before. We need to submit this once more, bright 0, bright 2, 4, and 6, and then dim 0, 2, 4, and 6. And then here we're going to check for type 3, and we're going to ask for effect size, summary for statistics for groups, and pairwise comparisons of means. And once more we have the results. The first thing that we get is some summary scores for factor 1, dim bright, and for factor 2, 0, 2, 4, and 6. Next we have some means and minimum, maximum, and standard deviation for each combination of dim, bright, and 0, 2, 4, and 6. And then finally we have some of the analysis of the interaction. Next we have comparisons for the main effect 0, 2, 4, and 6, where it is comparing each one of the different levels. And you can see that basically the only one that is not significant is the difference between 0 and 2, but all of the others are significant. This will be very interesting, except that we also know that we have a significant interaction, and that is the part that we have next. And just like we've done in the past, what it will be ideal is that we have a way to identify what specific combinations seem to be significant, and then to think along the lines of what is this really telling me as far as how the two factors are interacting with each other. However, the best way, at least that I know personally, to do this will be to create some kind of plot so I can try to identify what are the specific combinations that seem to be significant, and then in that sense to be able to make some sense of what this interaction seems to be saying. Again, it's just too bad that within R Commander there is no easy way to create this type of plots. And once more, my suggestion will be that once that you get more familiar with the R environment, that you look into creating some of these charts using some of the packages I mentioned, specifically ggplot2 and lattice. Those two packages create some really nifty plots that you can use to identify what seems to be going on. I think this is the end of this section, and with that I have concluded the demonstrations for how to use R Commander when you are interested in doing some analysis that will be appropriate for program evaluation.